next speaker this afternoon is Horatio Boedihardjo, lack of Gaussian Tail, or in the class around fractional Brownian motions.
Thanks. I'm just trying to put it in full screen. Can everyone hear me okay? Yeah, okay. So thank you to the organizers for giving me the chance to speak here. I will be speaking a lot about a tail probability of certain random variables. So I thought it was useful to spend the first slides just to fix the notion of tail probability. Different people have different precise definition of tail probability. All of them describe more or less the same thing. But I just thought I would fix sort of what we mean by tail probability in this talk. So suppose you're given a high multidimensional random variable x. The tail probability in this talk would mean the probability that the norm of your random variable is very, very large. So this tail probability is quite useful for a few things. It's useful for risk management. If x is sort of the number of patients coming into a hospitals, then you want to know what's the probability that there will be too many patients you couldn't accommodate, for example. So these tail probabilities, in theory, is also useful for to help you determine the existence of moments. So the faster the tail probability decay, the more moments a random variable would have. And in this talk, we'll be looking at two particular type of tail probability behavior. So one of the tail probability behavior that we'll be looking at a lot is the Gaussian tail. So here, when we say Gaussian tail, we're only looking at the upper bound of the probability rather than the lower bound. So we say a random variable has a Gaussian tail if the probability that the modulus of the random variable is very large is upper bounded by the tail probability of a normal random variable up to a constant. So when we say Gaussian tail, it means it decays at most at the speed of the Gaussian tail. So slightly more general than Gaussian tail, you can see that in Gaussian tail you have a k square in the exponent. If you replace the k square to a k to the power q, then you get the q Weibull tail. So q to 2 Weibull would be the same as a Gaussian tail, for example. So the random variable that we'll be particularly interested in is the solutions to differential equation driven by fractional Brownian motions, which you have seen in at least 2 talks today, in Peter's talk and also in Pablo's talk. So here we're actually going to just focus on differential equation that hasn't got a drift. So we are going to, because even in that case, the tail probability problem is already quite difficult. Of course, you can also ask the question when you add the drift back in. So we'll be looking at a differential equation, a multidimensional differential equation driven by a multidimensional stochastic process. There will be, it will be a multiplicative noise, so there will be a vector field in front, and we will be assuming that this vector field has bounded derivatives of all orders. And we also assume that you start from a deterministic initial condition. So for the driving process, it will be, you have seen from Peter's talk why we need to assume that the Hurst parameter has to be bigger than a quarter, and we'll be assuming this driving stochastic process to be d-independent fractional Brownian motion, and so that this differential equation can make sense in the sense of rough path theory, as long as the Hurst parameter is bigger than a quarter. So just a quick recap for those about what is a fractional Brownian motion. So it is a Gaussian process that starts from 0, and because it's a Gaussian process, to specify the process, you just need to specify its covariance function. And one way you can specify the covariance function is by specifying that the expected value of the square of the increment is of this form. And in particular, if h is a half, then you get Brownian motion. A lot of this talk will be looking at what happens when h is strictly less than a half, which is actually the case where it's more tricky to make sense of these differential equations. You need to make use of rough path theory. So we'll be assuming, so the tail probability of these differential equations actually will vary depending on the behavior of this vector field, and in this vector field, as in a lot of the rough path classical literature, we'll be assuming that all derivatives of the vector field is bounded. So the question we are interested in this talk is how do we find, for large K, the tail probability of the solution, or the distance between the solution and the starting points. So just to help us get an idea of what kind of tail behavior we should expect, we'll just be looking at, we start with a toy model, just a discretized version of the differential equations that we have just written down. So suppose you start from an initial deterministic condition, you look at the discrete differential of process A, you start, and that is defined as V of an times Zn plus 1 minus Zn. Zn's is a Gaussian process, meaning all finite dimensional distributions are Gaussian for this process, and assuming V is bounded. So this is just a toy model just to help us get an idea of what the tail probability would look like if you have a discrete model. So in this case, if we are interested in the distance of an from A0, then we can write that as a telescoping sum, and then we can bound each of these. So each of these terms in the sum can be replaced with this differential equation, and because the V is bounded, therefore we can bound each of these terms by m times the modulus of this Gaussian process, but increments of this Gaussian process. So you can see there's no, so you're just looking at basically sum of modulus of Gaussian random variables. There's no square, no cube in there. So because of that, you would expect that you can see that the tail probability of an minus a0 is actually has a Gaussian tail, and really the key here is that the V is bounded by m, which is what gives you the Gaussian tail. However, it's a Gaussian tail with constants that depends on n, which is the number of time steps. So you wouldn't expect this to automatically give you a way to study continuous time, because for continuous time you would have n would be kind of be infinite, because you'll be progressing forward in infinitely many discrete time steps, and then take limit as n tends to infinity. So this is just to give you an idea. You will need a different set of techniques for continuous time, and that has been studied in some parameters of H. So just to point out a very trivial example, that if your vector field V is constant, is identically equal to 1, then obviously then your y would be a combination of fractional Brownian motion, which is Gaussian, therefore your y would have Gaussian tail, obviously. And much less trivially is that if you have a Hurst parameter that is greater than or equal to half, a half is Brownian motion, greater than a half is a differential equation that can be made sense in the sense of Young. So in that case, in the Brownian motion case, it was very classical. There's the differential equations under the assumptions that all derivatives of the vector fields are bounded. Under that assumption, your solution will have a Gaussian tail. That is classical. I couldn't quite pin down who first proved it, but for example, Pusserkostruck has even a Gaussian tail bound for the density, from which this would follow quite easily, and they have it actually for more general class. They have the drift in as well. So for h bigger than a half, this is sort of the anomalous case. This is studied much more recently, because only in the way to define these differential equations in h bigger than a half regime, you need to use a paper from Lyons in 1994, and so that will give you, the Lyons paper will give you the existence and uniqueness of solution. Once you have that, you can study the behavior, and Baudouin or Yang-Tyndall tells you also that, that for h bigger than a half, the solution would have a Gaussian tail. So for h less, so And let me perhaps, before moving on, just to point out that this Gaussian tail is sharp in the sense that you can find an example, namely the constant vector field case, where this upper bound is actually attained. With constant vector field, it has Gaussian tail and it has a Gaussian tail upper bound, so you can't possibly improve k squared to something bigger. You can't improve k squared to k cubed, for example, because you have example where it's actually k squared. Now, the case h less than a half is slightly more tricky. You have to define these differential equations using the more recent theory of rough paths. So Karl's literary lions there's been a body of work looking into that, accumulating in the work of Karl's literary lions, who show that even when h is less than a half, you have an upper bound for the tail probability. But interestingly, it's no longer, they haven't got Gaussian tail upper bound. So because h is less than a half, so 1 plus 2h is less than 2, so you have an upper bound that is bigger than a Gaussian tail upper bound. So then that leads to a question, because we have seen that in the discrete time case, you have a Gaussian tail, h bigger than or equal to a half, you have a Gaussian tail, h less than half, you have a non-Gaussian upper bound, but is that because you can improve the upper bound so that it becomes a Gaussian tail upper bound, or is it because in h less than a half is genuinely a non-Gaussian tail? So this is sort of the question we're going to explore today, is whether we can find an example of a differential equation. Certainly these trivial examples wouldn't work, but can we find a slightly less trivial example where this upper bound is actually attained, or can we actually show that actually you can improve this? So the example we're going to be constructing is to use stochastic integration. So stochastic integrals actually can be seen as a solution to a particular type of stochastic differential equation. So we're going to be looking at stochastic integrals of bounded functions, just because the vector fields in the stochastic differential equations, we're assuming that to be bounded. So we're going to define this two-dimensional stochastic process, y1, y2. y1 is the integral of phi b2 db1, b1, b2 is independent fractional Brownian motions. y2 is just the second coordinates of the fractional Brownian motions. So these two together give you a two-dimensional process which satisfies a stochastic differential equations with this vector field. And this is, if you take, for example, phi to be a uniformly positive, phi to be a function that is bounded uniformly from below by a positive number, then this would even be an elliptic differential equation. So this is very, very non-degenerate. And what we're hoping to do is we're hoping to show that in this particular example, you get a tail probability that matches with the upper bound that Karl's literary lions give you. So before I move on to study more about fractional Brownian motion, the fractional Brownian motion case, I just want to look a bit more into the Brownian motion case and see why is it that in the Brownian motion case you get a Gaussian tail, and hopefully that will help us understand why do you get non-Gaussian tail when you change from Brownian motion to fractional Brownian motion. So let's, for now, just for this slide, we're going to look at the tail probability of integrals of Brownian motions against another independent Brownian motion. As before, as throughout this talk, we'll be assuming the function phi to be uniformly bounded by a deterministic number. So we'll be interested in looking at this tail probability of this integral phi y dx. And because you have two sources of randomness, you have got x and you've got y, and they're independent, one way you can simplify this problem is just by conditioning on one of the randomness, and then that will allow you to focus on dealing with the other randomness. So we'll first condition on y, and then that means basically we freeze y and we can choose y as a deterministic path because we're conditioning on y. So we're assuming y is known. And if y is a deterministic path, if we're conditioning on it, then that means this is now stochastic integral of a deterministic path against Brownian motion, which means it's normally distributed with mean 0 and a certain variance, a variance which will depend on y. And because this is conditioning on y, this is normally distributed, therefore it must have Gaussian tail, and the Gaussian tail would depend on the conditional variance of this integral. And this because it's Brownian motion, the conditional variance of this integral can be calculated very easily because it has mean 0, therefore the conditional variance is just the conditional mean square, and because you're conditioning on y and x and y are independent, therefore Ito isometry, so therefore you can treat phi ys as the deterministic function, deterministic path, and you can use Ito's isometry to calculate this as integral phi y square, and because phi is bounded by m, so then for this is bounded by m square. Now you can plug this bound on the conditional variance back into this here, and because, well, you can see you have a minus sign and sigma square is at the bottom of a fraction, therefore this is increasing in sigma square, therefore this is bounded by exponential minus k square divided by 2m square, so therefore you get a bound which is a Gaussian tail bound, because you have a constant times exponential of, you have a k square here, because, and everything else are deterministic. So this is this proof that the stochastic integral of phi x dy has a Gaussian tail if x and y are Brownian motion. So why do we expect something different for fractional Brownian motion? So if we look back at this calculation, so the conditioning step, you can still do it for fractional Brownian motion. You can do it as long as x and y are independent. So this step, this second step, you can also do it because for fractional Brownian motion, it's still true that if you freeze y, the rest would be Gaussian. The thing that gives you a Gaussian tail is the fact that you have a Ito isometry giving you that expression, and so the conditional variance is uniformly bounded, and that is why you get a Gaussian tail for Brownian. So in order to try and prove, so this seems to suggest that in order to try and show that fractional Brownian motions integral would give you non-Gaussian tail, we would need to try and show that the conditional variance is unbounded. If it were unbounded, then there's hope that perhaps this, if we calculate it, this would give us a non-Gaussian tail, a Weibull tail. So, to do that, in order to show that the conditional variance for integrals of fractional Brownian motions are unbounded, we need to see whether we can calculate this. And as Pablo mentioned earlier, today in the morning session, there is a way to write down this conditional covariance. So we're now into the case where we have independent fractional Brownian motions. There is a kind of Ito isometry formula for fractional Brownian motions, and this is the formula for h less than half, a separate formula when h is bigger than a half. So therefore, our goal now, we've mentioned that if this were bounded, then you have Gaussian tail. We don't want a Gaussian tail, so we want to show that this is unbounded. And in fact, if we want to get a matching lower bound for the cast literal lines upper bound, then we need to get this lower bound for the tail probability of the conditional variance. So we start off with a problem about conditional variance of integral phi x dy. We reduce that to a problem about tail probability for sigma y square, and we have made some progress because we start with a random variable that depends on x and y, as two sources of randomness, and now this is a little bit simpler because it's just a function of y. So how do we study the tail probability for this random variable? So notice that this random variable is actually a function of a Gaussian process y. So there is fairly standard results about how to study the tail probability of function of Gaussian random variable. So suppose, let's take a very simple case just to illustrate the idea. Suppose you have a standard normal random variable and you have a function from real to real. Suppose you know that the function grow as big as z to the power alpha, then it's very easy to show that f of z has a tail of 2 over alpha Weibull tail, at least bounded below. So therefore, in a sense, in order to understand the tail behavior of this random variable, which is a function of the Gaussian process y, all you need to do is to see how this function grow when y is large. But what does it mean? So y is a stochastic process. What do I mean when I have y is large? Because y is a Gaussian process, so you can actually move the Gaussian process around as long as you're translating in the Cameron-Martin direction. So what I mean by f growing very quickly, what I mean is that if you take your y and you take a Cameron-Martin path h, so for Brownian motion, this would be all the paths, all the functions whose derivative is in L2. For fractional Brownian motions, it's more difficult to describe, but there is various known facts about them. So if suppose you have a Gaussian process, and suppose there is abstract Wiener space associated with this Gaussian process, if your function f grow basically linearly, then with a Gaussian probability, then f of y would have a Gaussian tail. And in fact, you can, using this lower bound, you can show that if f of y grow like lambda to the power alpha, so if you replace this lambda with lambda to the power alpha, then this would become k 2 over alpha, just like in the one-dimensional theorem that we've just mentioned. So in other words, if you have a Gaussian process y, and you want to look at the tail probability of f of y, you just really need to look at how quickly f grow when you translate y in the Cameron-Martin direction, times parameter lambda, which you're going to take to be very large. Or in other words, if your Gaussian process has more, and this comes back to the question of what makes the difference between why do you get different behavior for Brownian motion compared to fractional Brownian motion, is because the fractional Brownian motion has a larger Cameron-Martin space, so there's more h you can choose, which means according to this criterion, there's more you can choose. So for different h, you could get a different growth rates here. So for some h, maybe you get lambda. For other h, maybe you get lambda square, for example. So if you have a larger Cameron-Martin space for your Gaussian process, then there is more possibility for this quantity to grow faster, and then you get a heavier tail as a result. So that really is part of the reason why you have a different tail behavior for fractional Brownian motion, just because it has a larger Cameron-Martin space. It's one way to look at this. So this quantity fy plus lambda h is quite tricky to study a lot of the time because y is random. You don't actually know what y is. So there's one very nice property of the particular function that we're looking at, which is that it's actually for large lambda, sigma of y plus lambda h is roughly the same order as sigma of lambda h. So the way we prove this is basically we look at the difference and then do some technical analysis to show that this is bounded by something that is not too big. So then the question now is reduced completely to looking at how quickly the sigma of lambda h grow as lambda tends to infinity. So let's see how sensitive that is to the Cameron-Martin path we choose. So suppose we take a Cameron-Martin path ht equals to t. So Cameron-Martin space of Brownian motion definitely contains that, and Cameron-Martin space for h less than a half is even bigger, so we also contain that. So if we do that, we can substitute this h into the formula we have got, and we'll get a growth rate of lambda to the power 1 minus 2h. So notice when h is a half, there's no growth, which is why you get Gaussian tail. But this actually would already give you the this is good because at least it's not bounded, but it's not enough to give you a tail probability that matches the cast literal lines upper bound for tail probability. So you need to choose another Cameron-Martin path to make it work. So recall what is the random variable we're looking at. We're looking at this particular random variable, and well, just by looking at this, how do you make this bigger? One way you can make this bigger is by choosing a h. Well, is by choosing a top that is more irregular. So because you're dividing by t minus s, so in some sense this is a little bit like calculating the derivative of phi. So phi composed with lambda h. So if you want to make the derivative of this bigger, one way to do that is to choose a more irregular function, h. How irregular can we choose h to be? That will depend on how big the Cameron-Martin space is for your fractional Brownian motion. In fact, it's known that fractional Brownian motions, Cameron-Martin space contains all Holder continuous functions with Holder exponents h plus a half plus epsilon. So we want, in order to make this as big as possible, we're going to choose a Cameron-Martin path that's as irregular as possible, and that means choosing a Cameron-Martin path that is almost h plus a half plus epsilon Holder continuous. So, and in particular, we don't want to choose a path that's differentiable, and that's what makes it difficult to choose a Cameron-Martin path. We want to choose a function that's nowhere differentiable. It's not enough to choose a function that is has a singularity at one point. You actually, to make this big enough, you need a nowhere differentiable function. So then this is a textbook nowhere differentiable function, Weierstrass function, and the reason why this is chosen is also that it has a lot of very nice property. So in particular, it has this scaling property that if h of 2 to the power minus kt, this property is a bit like the scaling property for fractional Brownian motion. You can move the scale outside the path at the expense of multiplying, raising the exponent to power alpha. So that's one nice property of the Weierstrass function. And with this property, we can try and understand what this quantity is. So what we want to do basically, I mean, the idea is that we've got a lambda inside phi. Mathematically speaking, what we're trying to do is we're trying to move the lambda here outside to the integral, because that's how, because ultimately we want to show this is bigger than or equal to lambda power something. So we want the lambda to basically come out. But this phi is a highly nonlinear function. So the way we actually do that is we do a change of variable. So t, replace t with 2 to the power minus n times t dash. And then if you do this change of variable, that basically has the effect of taking out lambda, because you can choose an n large enough so that lambda 2 to the power minus n alpha, you can choose an n so that this is actually bounded above and below. And then because of the change integration by substitutions, you got these factors coming out. And just to help simplify an understanding of this integral, you can also do a change of variable t minus s equal to u. That's just for computational reason. So then once you have that, another thing to observe is that the key contribution to this integral is when t and s are very close, which corresponds to when u is very small. So actually, rather than integrating from 0 to 2 to the power n, we can throw away the part from 1 to 2 to the power n without losing any order. So basically, we can replace the 0 to 2 power n with 0 to 1, and that, it turns out, doesn't actually lose any order of magnitude, which is interesting. So that really shows the key contribution come from the diagonal of this integral. So then once you have that, you need to use another property of Weierstrass function, which is that you can split the Weierstrass function into two parts. One part is globally Lipschitz with Lipschitz constant, I think it's Lipschitz constant 1, I think. And then the other part is actually nowhere Lipschitz, nowhere differentiable, but it is very conveniently one periodic. So then this is just copying from the previous slides. So we're trying to bound this from below. And what we can do is that we can split this inner integral into sum of 2 to the power n integral, where we go one step at a time. And then we just need to find a lower bound for this. And this is where we need to assume something about phi dash. So remember I mentioned, if phi were a constant, you're in trouble, because I mean we're interested in something like integral phi y dx. So if phi were a constant, then you just get x, which x is a Gaussian process, so you get a Gaussian tail. So if phi were a constant, then you would get a Gaussian tail. So to get a non-Gaussian tail, we must assume some non-decaying condition on phi, on the derivative of phi. So we're going to assume that phi's, well, let's assume phi's derivative has some lower bound. And we're going to assume, as we have mentioned before, we're going to make this of order 1. So we're going to assume 2 to the power n alpha has the roughly same order as lambda. So then by assuming non-decaying condition on phi dash and using mean value theorem, you can show that this difference is have the same order of magnitude as ht plus k minus u. And actually now, H has two parts. Remember, H has a globally Lipschitz part and a part that is very non-Lipschitz. And in fact, this difference, the non-Lipschitz part is going to dominate because this difference here, the globally Lipschitz part, this is going to be like a modulus u. But if you have a nowhere differentiable one, this second part will actually contribute u to the power a fractional power. So this part is actually going to dominate over this when you look at the increments. So therefore we just need to look at the difference for this. But this part is periodic, therefore it's independent of k. Therefore, roughly, these two are of the same order. You can remove the k, and you have roughly the same order of magnitude as basically the difference of because the dominant part is this part here. So and this you can get a lower bound using some properties of a Weierstrass function. So therefore, basically, I mean, the key here is that this. So what this calculation shows you is that although there is a k here, this integrand, the order doesn't depend on k. This integrand have roughly the same order regardless of what k is. So therefore, you would have 2 to the power n things that are non-zero, that are uniformly positive. So then if you put 2 to the power n here, then you get 2 to the power n times 1 minus 2h. And because we're assuming lambda is of the same order as 2 to the power n alpha. Therefore, you get this growth in lambda, which is exactly what's necessary to get a matching lower bound for class-literal lines. So in other words, in order to show that sigma square y has the tail probability we want, we just need to show that it grows fast enough when we replace y with lambda times h. So here is sort of just quick summary of what we've done. So what we've done when we try to study the tail probability of this integral is that we first condition on y. So then that translate the problem of bounding this from below to a problem about bounding the conditional variance of this from below. So we just need to bound this part, and then this sigma y square has an Ito isometry for fractional Brownian motion, and then to show that to study the tail probability of this sigma y square, you just need to look at what happened when you translate y by lambda times a Cameron-Martin path, and it turns out that these have the same order as sigma square lambda h. So you just need to work out the order of sigma square lambda h, which is what we've just done here. So then this is the main results that we managed to prove. So we managed to prove that assuming that you have a function that is C infinity bounded derivatives of all order, and suppose that it has a non-decaying derivative. So one example of a function that satisfies this is the sine and cosines would satisfy this. Under this condition, if you have independence fractional Brownian motion, then we can show that the tail probability of integral phi y dx has a Weibull lower bound for beta Weibull lower bound for any beta strictly bigger than 1 plus 2h, and if beta were equal to 1 plus 2h, then this would match the class-literal lines upper bound. So that in particular shows that the class-literal lines Weibull upper bound is actually sharp for h less than a half. The solutions to differential equation driven by fractional Brownian motion with a bounded vector field indeed has a Weibull tail. You can't prove it doesn't have a Gaussian tail. So the next step, I think, would be really interesting if we can generalize this to differential equation. So we've studied the tail probability of a stochastic integral. Would be interesting to study the tail probability of solutions to differential equation driven by fractional Brownian motion in general with bounded vector fields, but yeah, we didn't manage to do that. I mean, it's just to list some of the difficulties. I mean, you have to choose. There's some conditions on V. If V obviously, you know, there's a few V we know wouldn't work. So if V are constant, then you have Gaussian tail. If V is compactly supported, then Y would be compactly supported because you have a dynamics. So you have a So if you have a dynamics here, so suppose your V is supported on here. So as soon as your dynamics reach the boundary of the support for V, then you will stop moving, because once you reach the boundary of the support, V becomes 0. So then for Y become constant. So if you have a V that is compactly supported, then Y would also be compactly supported. So it's not clear what's the correct condition on V that would ensure you get non-Gaussian tail, but that's yeah. So and then the other, I think a lot of what we have discussed will still work in the sense that we need to study what happens when we translate along Cameron-Martin path, but I still think Weierstrass function would be a good choice, but then you have a much more complicated function, so it's not very clear how you can study the behavior of y as lambda tends to infinity for this differential equation, just because it seems to be a bit more complicated. So that's all I want to say. Thank you for all of your attention.
Questions?
I really like the talk. I like the use of camera marking is less construction very much. From a SD point of view, when you're doing Brownian motion to get the Gaussian tail, you don't go way too fast, too quickly. One can use E2 formula. On the conditions you have the solution has exponential moments. So then that would give the Gaussian bound straight away. So that's for the SD one. So for your case, I was wondering the same thing would happen. There's no, there are E2 formula allow you to calculate things. And it's possible, you see this equation you write down?
Yeah.
If you differentiate with respect to lambda, and you get the Malevin derivative of the solution of stochastic differential equation.
Yeah. And
if you control the derivative, make sure it's going fast, like the moment of it is going sort of super exponentially, might be something related to moment unstability of that system. This comment.
Yeah. I think you're right. So if we can get a lower bound for the Malevin derivative,
which is related to the derivative in the non-Malevin sense,
which is
the linearization.
Yeah.
The equation of the linearization is related to that one as well.
Yeah. Okay. So I think So if we can get that lower bound, then I think we are good. So it's just there isn't as much work on lower bounding solutions to RDE to differential equations. So that's exactly the place we're stuck. Trying to get a lower bound for differential equations driven by fractional Brownian motions. I think
because somehow you can write down explicit, implicit solution for YT.
Yeah.
That allows probably to play something low.
But just by differentiating with respect to lambda. That's interesting.
All right, any more questions? Okay, so let's have a coffee break.